All right, so let's go ahead and start off with any questions from you. Do you have any questions you'd like me to look over, or any particular example? And we can try to do an example of the topic you would like. And if you don't, yeah, so you can go ahead and try to find one. Or I saw a hand back here. And I was thinking that the rest of the time we went through these ones really quick. So I was going to go in detail, like by hand, how to do some of these instead of just the calculator commands only. So we won't do any of that. And I've got an example here that we can do. But do you have your question back there?
Yeah, I was just curious if you go over
One more time.
you could go over the testing
Oh yeah, how to find those hypotheses?
Yeah.
Like how to write them out correctly? Yeah. All right. So let's do. All right, so let's do a hypothesis test. Do you care if it's with proportions or means? Yeah. All right, let's do one with, let's start off with proportions and then do one with means. Question? Oh, there we go. Nice. All right, awesome. Yeah, okay, so let's maybe see percentage of, I'm trying to think of a topic here. So, does someone have a good proportion topic? So let's try, I'll crowdsource here. Maybe how many people are sick? How about that? I'm sick. I hope you stay healthy. So if you really want to stay healthy, just don't get too near to me. All right, so assume the proportion of college students who have the cold today is, would you believe 10%? Maybe a little lower. How about 5%? Is 0.05. We wish to see if University of Montana has a different proportion of students who have the cold. Have a cold, maybe not the cold. So we take a sample of 300 students. Take a SRS of 300 students. And 20 of them have a cold. So perform a hypothesis test. That's the problem. All right. So first thing we want to do is we want to set up our hypotheses. So there's always a null, always an alternative right off the bat. All right, and now we have to think about what the parameter is. So the parameter, it's a proportion. So it's proportion of college students who have a cold. With the null hypothesis, we always have equality. So we think, oh, the proportion is 0.05. And then the alternative would be that it would be different than 0.05. Or in other words, it's not equals to 0.05. Right? So yeah, this is a proportion. Any questions so far? Yeah, because you gotta make sure you get this is super key right here. That you get the right symbol here, either like greater than, less than, or not equals to.
How do you know it's not equal to greater than?
Yeah, so you have to read carefully through the problem. In this problem, it says different. So that means we don't know in which direction. But some problems they'll say like greater, or they'll indicate some kind of direction. So you think that the proportion is bigger than 0.05 or maybe less than 0.05. But if it's just, is there some kind of change or is it different? That's the not equal. Okay. All right, so now we want to, well, you want to make sure that you could use the central limit theorem. I'm going to kind of gloss over that because it's, I mean, yes, it's necessary, but it's kind of harder to test on that little tidbit in this problem. But we would need to get, well, first let's find the observed proportion, so p hat. And then that will allow us to find the, we could find the z-score, or the test statistic. So here we had 20 out of 300. And that gives us a proportion of 0.067. All right, so now let's go ahead and find the test statistic. Well, it's actually best. Let's draw a picture and then let's find the test. Let's find a test statistic and then draw a picture. Definitely want to draw a picture. All right, so this is on the green inference summary sheet. So we've got it's p hat minus p naught all over the standard deviation of p naught times q naught over n. That's what it is. So we've got 0.067 minus, and p naught comes from, it's this number right here, 0.05. And then this would be 0.05 times 1 minus 0.05, which is 0.95. And then n is 300. All right, 0.067 minus 0.05 divided by square root 0.05 times 0.95 divided by 300 gives us 1.351. All right, so now let's draw a picture. 0, 1, 2, 3, 2, 1. This is a standard normal distribution. So since we went through the trouble of finding the z-score, let's just use this picture. So we've got 1.35 is right about here. That's 1.351. All right, so now we want to shade to the right, but then this is two-sided, so we want to have a tail on the left as well, which is negative 1.351. It's right there. So shade to the right, do shade to the left. There. All right, any questions so far? Crystal clear, nice. It's like a mountain spring. All right, that's great. Okay, so let's find a p-value. P-value is equal to 2 times, and we're using normal CDF now because we got a normal distribution. From 1.351, 10 to the 99th, 0 and 1. All right. Got 0.177. So you see that I multiplied that by 2, so try not to forget to do that. 0.177. Now let's go ahead and make a conclusion. Would you like me to interpret it as well? It's going to get a little confusing. So let's do the conclusion first and then interpret. So since I already wrote this. Okay. Since the p-value equals 0.177 is large, we have no evidence oh, yes. There we go. No evidence. No evidence in favor of the hypothesis. That the proportion of UM students who have colds is different than 0.05. All right. Question. Yeah.
So what do you consider a large p-value?
Oh yeah, so 0.1 is so it goes back to in the notes where we had a bunch of different values that meant different things. So anything bigger than 0.1 gives you no evidence. Between 0.05 and 0.1 is suggestive. Less than 0.05 is moderate. Less than 0.01 is strong, and then less than 1,000th is very strong. So that's the breakdown. So.
I did the one proportions in the test, and the numbers are just a little bit different.
Oh, how much different? Like, I hope they're not like a lot different.
My Z-score for test statistic was 1.325.
Oh, okay. That's not alarming at all. That's see that just being a rounding issue. So it's within about 200, so that's not so bad. So as long as you you want to write down that you used the calculator command and that you got that. So, right? Yeah. Oh. Let's check it. Whew. Testing. It's good. All right. So let's do a interpret the p-value. So what does that number 0.177 means? So the p-value 0.177 means there is a 17.7% chance of getting a sample of 300 students with a proportion of as extreme or more extreme a proportion as 0.067 assuming the true proportion who are sick is 0.05. All right. So since this was two-sided, we have this extreme or more extreme part right there. And then also don't forget to mention that you're assuming the null hypothesis is true. So yeah, that's how we got our our drawing, our picture. So that's any questions on that? So what do you say? Let's do one with means, hypothesis test with means. And we can get creative and we can make a problem up here. Let's see, what's a good, do I have one? Yeah, I've got one about bus seats. Let's do that. Okay, hypothesis test. Testing means all right, so a bus has 32 seats on it, and it is assumed that a bus seat lasts for an average of 5 years. All right off the bat, notice we're using a quantitative variable. So we got five years. So we're measuring how long do these bus seats last for. This takes me right back to my childhood. Yeah, the bus seats in the public buses so much better than those yellow school buses. It's like big step up. It's nice. All right. So let's do a test. Let's test a bus. Okay. So we this would be kind of hard to do. I guess you'd want to do some kind of like have some kind of robot, like do some really fast wear upon the seats, and instead of waiting 5 years, and then maybe like translate that into real life somehow. I think that's how they test these things. Like I've heard of companies doing seat testing. They have machines that just like sit on chairs all the time, just like in a rapid progression. You know? Just like, all right. So we test a bus, and we find a sample average of let's do 5.5 years, and a standard deviation of 0.88 years. Is this bus I think there's a better way to say that. So we want to show that this bus exceeds the standards of bus seats, bus seat durability. All right. So that means that we're hoping, well, the null hypothesis would be that that there is no difference, that this bus is, or that the average really is 5 years. But then the alternative here is that we're exceeding that, or that the seats last longer than 5 years. That would be the alternative. All right, everybody see that? So there's this word exceeds. That's what gives you the direction of the alternative right there. All right, so the parameter here, it's means. So we're doing mu. We have mu. So either mu is equal to 5. That's what we think it is. That's what we're assuming. Or mu is greater than 5. So I guess in the problem statement, it would be better that to say that the company or the bus, people who make the bus seats, they want to get at least average of 5 years. That's their standard. So. All right. So any questions with this? This is again super important to get those correct, or else all the numbers in your the work after this is going to be a little off. So. All right. So let's find a test statistic. Yeah, let's do a test statistic. And then this one we have to realize, okay, is this like going to be like a t distribution or normal distribution? So when you're thinking about this problem, you'd be like, okay, all right, which one do we do? And this one, since it's working with means, it's going to be t distribution. That's what it's going to be. And in this standard deviation here is S. That's from the sample. Right there. All right. So we're going to find a test statistic of t. And we're doing this for means. So you could look on your green inference summary sheet and track down where that t equals something. And what that is you use the y bar, which was 5.5. Or let's just write out the formula. Y bar minus mu naught S over square root of n. All right. Any questions with that? All right, so that would be 5.5. Mu naught is 5. S was 0.88. And there's 32 seats on the bus. So we looked at one bus, one whole bus. So square root of 32 there. (5.5 minus 5 divided by 0.88 divided by square root of 32. 3.214. This is looking promising. 4.49. Do you have all your parentheses here? I got one set of parentheses up. Well, it's kind of hard to see. Okay, one set of parentheses in the numerator. And then two sets in the denominator, one for the square root and one for the denominator. So try just typing it in again. You still getting something different? How's everybody else doing? If anybody else has got the same thing as I got. Doesn't mean we know for sure, but yeah, we need to get at least like 15 people. We could do a hypothesis test on the number here. See if we got the same thing. In that case, it would be with a proportion, because it's a yes/no if you got the same number as I did. So, yeah. You're kind of better now?
Yeah.
Okay. All right. 3.214. All right, so now let's find the p-value. 0, 1, 2, 3. This is a t-distribution. Degrees of freedom is 31. 3.214 is right here. Okay, so we look at our inequality to see which way we shade. We shade to the right because it's greater than. All right, and now we do TCDF. 3.214 to 10 to the 99th. Degrees of freedom of 31. This is what our p-value is. All right. Three 3.214, 10 to the 99th, 31. Should be small. All right, and it's 0.0015. Yeah, that's good. 0.0015. All right. So our conclusion here is that there is strong evidence in favor of the alternative hypothesis, which is that there is a higher average than 5 years for these bus seats. All right. All right. So, are you guys happy with hypothesis tests? Do you want to do another one, but with like two samples, like either a 2 proportion or a 2? Maybe we can look at the one from the book too. No, let's just come up with another problem. Does that sound good? Does everybody get that? Oh yeah, let's do 2 proportion then. Yeah, because that'll be a good one. Oh, and we haven't even gotten confidence intervals yet. We'll come around to those. So 2 proportions. All right, so now let's try to think of, if anybody has a good idea with different proportions to think about. Let's see. What about weather? So let's compare the weather of Missoula with the weather of Great Falls. Proportion of sunny skies. So days of the year with sunny skies. And then we want to see if there's if Missoula has a higher proportion of sunny skies than Great Falls. So, all right. Okay, so yeah, let's write all this down. Okay. The proportion of days, and I'm just going to completely make up these numbers, by the way. In in 2019 that were sunny. Like if you were to write a paper, you'd want to try to like be a little more rigorous with your definition of sunny. But let's just go with it. All right, so proportion of days in 2019 that were sunny in oh, how about this? So we have to find the proportion because this will be easier to state. So the number of days in 2019 that were sunny in Great Falls was, and in Missoula were okay, I gotta get some convincing numbers now. We're, how about 150 and 180 respectively. All right. Differences. There is a difference. All right, so we got that. Is Missoula more sunny than Great Falls? All right. So with this one, we've got two proportions here, one from Great Falls and one from Missoula. They both have the same sample size because they both have the same number of days in a year, so 365 days. We're just looking at all the days in the year. So let's go ahead and find. Let's define the parameters because it's with the two proportions. It's really good to keep them straight, like which one's P1, which one's P2. So let's say P1 is the proportion of sunny days in Great Falls. And P2 is the proportion of sunny days in Missoula. All right. So now we know we have that straight, and we're interested in like P1 minus P2. Is that going to be equal to 0, or is it going to be well, in this case, it would be less than 0 would be the alternative. All right. So we've got H naught is that their difference, P1 minus P2, is equal to 0. And then HA, we want to make sure this works out to being Missoula is more sunny than Great Falls. So that means that the bulb just, maybe the light bulb just went out. Huh. Oh, I don't know what happened. I hit the button again. We'll see if it starts up. Well, anyway, so P2 would, we want P2 to be larger, which would give us a negative number. So that would be P1 minus P2 is less than 0 would be the alternative. We're at about 50% here with the startup, it says. So. Okay, so after that, let's go ahead and find what P1 hat is and P2 hat is, and then we can find the observed sample difference to what the P1 hat minus P2 hat is. So try to follow along on your paper. So try to find what P1 hat is. So P1 hat would be referring to Great Falls, a sample from Great Falls. And there were 150 days out of 365. All right. So I'm gonna just I'm gonna do the rest on the board, I think. Yeah, without a projector screen. So yeah. So for those of you listening to the recording, the projector light bulb went out, and I'm doing this on the whiteboard now. Right. Okay, so we've got H naught P1 minus P2 equals 0. The alternative is that the difference would be negative, or in other words, this would be less than 0. Anyway, so P1 hat is 150 over 365, and P2 hat is 180 over 365. Let's find that. So we've got 0.411 and 0.493. And now we find the difference, P1 hat minus P2 hat. And that's negative 0.082. All right.
Why was the second hypothesis less than 0?
Oh, right here?
Yeah.
Yeah, so so there was a word in the problem statement. It was, is Missoula more sunny? So maybe I could write that again. Yeah, so it's just getting that straight. Missoula more sunny than Great Falls. All right, so now we want to find the test statistic. And to find the test statistic, we use something called p hat pooled. P hat pooled. So let's go ahead and find that. P hat pooled. So what that is it's the idea of combining your samples together or pooling them together, and then seeing how many successes you have out of that new pool. So here we have 150 plus 180 over 365 plus 365. So that's our pooled p hat. 50 plus 180 divided by 730 452. And we use that to find our standard deviation. Or no, our standard error. It's called, I think it's called the standard error. Anyway, so we have this. We want to find our test statistic like we've been doing, and then we find the p-value. All right. So test statistic. In this case, we're using a z. Since we're working with proportions. Question?
For p-hat rule, can we also just like add together the p1 and 2 values like 0.411 and 0.493 and then divide by 2?
In this case, it would work, but if the denominators are different, it would not work. So this is a rare case where you could do that. I think it would work out to do the same. Yeah. So don't do that in general. All right. So now we use this big the big formula here. So we've got well, it's what it is. It ends up being this. So p1 hat minus p2 hat all over p hat pooled, q hat pooled all over n1 plus p hat pooled, q hat pooled all over n2. Any questions with that? That's the right formula, right? You check on your green inference summary sheet. Yeah. Oh, yeah. I should mention again why we're using pooled is because we're assuming there's no difference. So our alternative hypothesis, our null hypothesis, we're assuming this. So we're assuming there's no difference between these proportions, and so we can just pool them. It's okay to pool them. So we've got negative 0.082 over the square root of 0.452 times 1 minus 0.452 all over 365 plus 0.452 times 1 minus 0.452 again over 365 again. Questions with that? So this number is from the pooled, the p hat pooled right there. And you find the q hat pooled, you take 1 minus that. And I'm just going to put it all in my calculator all at once. So let's do that. You can do it however you do it, see if you get the same thing as me. Plus. I got negative 2.226. I did that right. All right, so now this is the difference. Well, it's just the standard normal distribution. 2, 3. Any questions with that? Okay, cool. So we're wondering if Missoula is more sunny. In other words, we're shading to the left. So you always want to look back there, shading to the left. and we can use normal CDF to find the p-value. Normal CDF, negative 10 to the 99th to negative 2.2260 and 1. Question?
What is the instance that you multiply?
Oh, yep. So that only happens if you're doing a two-sided test. And that's if you have a not equal sign right here. So, and what that is that you have two tails, like here and here, because you don't know if it's going to be bigger or less. Okay. Yeah, let's do that. All right. 6. I got 0.013. All right. 0.013. Okay, so that's moderate evidence. So is moderate evidence that Missoula is sunnier than Great Falls. Yeah, I can write that out. There is moderate evidence p-value equals 0.013 that Missoula is sunnier than Great Falls.
Are you going to give us an alpha level to decide if we reject or?
I may. So you may either do, this would be the subjective view, or you may have questions about the decision-making view with the alpha level.
Yeah.
So with this, if I gave you an alpha level, I would send it back here. So before we go right through all that, so it'd be something like. You could just say it. You set an alpha level of 0.05. So with this, you'd say, well, since our p-value is less than our alpha level, you would reject the null hypothesis or accept the alternative. All right. Any other questions? Okay, so let's do one with the. I've got one about what 3 things does the central limit theorem tell you, and then we can do some confidence intervals. How's that sound for a plan? Question?
Quick question: is it okay to write null hypothesis P1 equals P2 and alternative as P1 is less than?
Yeah, that's totally okay, and that's the way your calculator does it. But it's just easier for me. So this is my personal preference. So P1 equals P2. This is less writing, but I just find it more confusing actually. But this would be like, okay, so these two proportions are equal, and then this would be that the proportion here is less than this other proportion. So, okay. All right. So let's go back to let's do back to the bus here, the bus seats again. I'm just curious if this actually. Okay, so so back to the bus seat problem. We've got we had n equals 32. We had mu equals 5, and we had sigma. Well, this is new information here. Sigma, this last one, sigma equals 1, right there. So this was the bus seat. So what three things does the central limit theorem tell us about, oh, hey, it's back. All right. I'm just going to go back over here. For those of you listening to the recording, apparently the projector screen was just overheated, so it's cooler now. All right, so yeah, what three things does the central limit theorem for means tell us about the sampling distribution of the sampling means? So this is just, you just write it with symbols is the easiest way. So the distribution, the sampling distribution of y bar is approximately normal, centered upon the 5, and with the standard deviation of 1 over square root of 32. So this is sigma. In this problem, sigma was 1. I gave some extra information here. And this was mu right there. So when we first looked at this bus seat problem, we didn't have this sigma. We just had an S from the sample. Now we have a sigma from the entire population. We think this is how it's how the spread is for this distribution. And this would be equal to 1 divided by square root of 32, which is 0.177. So problems like this, they're pretty straightforward. You just have to remember to divide by the square root of n here, not to use the original sigma, because this is the standard deviation for the sampling distribution, not the population's distribution. All right, questions with that? All right, so what do you say? Let's do some confidence intervals. Let's do one where we have to find the sample size. So let's say we have a confidence level. We're given the confidence interval, and then we find, okay, what kind of sample size do we need to get this? Kind of like that in that homework problem. One of our homework assignments, the hand-in homework. All right, so let's say that we have, let's say we have a confidence level of 99%. So what sample size do we need to get a confidence interval of, let's say, like hey, I don't think we've done this with means yet, so let's do it with means. So 235 to 270. So let's say that was our confidence interval with a confidence level of 99%. And we would also need to know the standard standard deviation, and S equals, let's just say 50. S equals 50. All right. All right, so this just uses a slightly different formula. This uses the y bar plus or minus, and with this one, yeah, this is a t star. Oh, we would need to know the sample size too. And n equals, no, we're finding the sample size. Okay, so if you knew t star, you would know the sample size. So let's do it with sigma instead. So then we can use z star. Okay, so if you know sigma, you can use some normal distribution instead of the t distribution. All right, so that's our problem. Okay. Any questions with that? Okay, so this uses sigma 50 over square root of n. That's what our formula is. Well, some of it. It's like a. Well, let's just do it all unknowns or not. So here, let me just rewrite this because it's a little sloppy there. Sorry. Z star times sigma over square root of n. There we go. That's better.
Is that on the green sheet?
I do not believe so. So a little extra tidbit for you here. So it's the difference between using a t distribution and a z and the normal distribution is what's going on here. So it's really like the one with the t star confidence interval, so one mean, but instead of a t star, it's a z star because we're using a normal distribution, and then it's with sigma instead of s because we don't have that extra variability introduced by estimating for the standard deviation. All right, so with this one, we know that y bar is precisely in the center of this confidence interval. So yeah, let's just draw a little picture. It goes from 235 to 270. So precisely in the middle of that would be 270 plus 235 over 2, which is the same thing as 505 over 2, which is 252.5. Right. So that's what y bar is here. This is our confidence interval. That's what we know. Z star, I think is it 2.576, right? It's on a table on your. Okay, so Z star 2.576. We know sigma, and we're trying to find square root of n. So we can find what the margin of error is, and let's work off of that. So that's going to be our strategy here. So the margin of error is this right here. That's the margin of error, and it is also precisely half of the confidence interval, margin of error, which is half of the difference of the upper bound minus the lower bound is 17.5, I do believe. All right. You guys with me so far? For the most part. So the overall strategy here is to find n. So if we could write some kind of equation with n in it, and then all the other parts of the equation are just numbers, like known values, then we should be able to solve for n. So that's the strategy here. So right now our equation is that the margin of error equals z star times sigma over square root of n, and we now know all of these but n, and let's just solve for n.
So you just substituted y bar for me. Where did the y bar go?
Oh, that was actually extraneous.
Okay.
I was just I don't know, just it's a side bit there, I guess.
Okay.
We don't actually need to know y bar in this problem. But it could be a potential question like, oh, what is y bar or something like that. So, all right, so this is 17.5 equals 2.576 times 50 over square root of n. Okay, so let's multiply both sides by the square root of n. I mean, there's a lot of ways you could do this, but let's just do it this way. So those cancel. And let's divide both sides by 17.5. So now we have the square root of n equals 2.576 times 50 over 17.5. We square both sides. And we get n equals all right, 2.576 times 50 divided by 17.5 squared. About 55. We want to be a little bit more conservative, so we round up 55. Right. Okay, any questions with that? Okay, so let's do some other confidence intervals, but let's also write out what they mean. All right. So let's maybe do a confidence interval for some of. Let's reuse some of these ones. Let's do a confidence interval for this hypothesis testing. I think we can do that. So confidence interval. This is with two proportions. All right, so we look at what the formula is, and we have to decide upon what confidence level to do. So let's say it's asking for a 95% confidence level. So find a 95% confidence level confidence interval. All right. or a confidence interval with a confidence level of 95%. So. All right, so here we've got the formula is P1 hat minus P2 hat plus or minus Z star. And here we can't use the pools anymore because we're not making that assumption. We're not assuming that the two proportions have no difference. We don't really know that yet with the confidence interval. So we would use P1 hat times Q1 hat all over N1 plus P2 hat times Q2 hat all over N2. Use that right there. Right. And I can't remember what P1 hat and P2 hat is, so let's just find them again. All right. So P1 hat, P2 hat. Okay, so we had 150 over 365. So 150 days out of the year for Missoula. No. Great Falls. 0.411. And then Missoula was 180 out of 365. Which was 0.493. So Q1 hat is 1 minus 0.411 or 0.589. Q2 hat is 1 minus 0.493 or 0.507. Right. All right, so the critical value would be a 1.96 for a 95% confidence interval. This difference here, well, let's just plug in these individual values because I don't remember what that was either. So, okay, it's 0.411 minus 0.493 plus or minus 1.96 times the square root. And then we have 0.411 times 0.589 all over 365. And then we've got 0.493 times 0.507 all over 365 as well. Right there. And then this can be a little bit of a pain to put in your calculator, but let's try it. All right, so we've got 0.411 minus 0.493 minus 1.96 square root 0.411 times 0.589 divided by 365 plus 0.493 times 0.507 divided by 365. All right. Any questions with that? And then you can do the same thing, but now let's just add instead of subtract. So just second enter that. All right. And that would be your confidence. Right. So we've got negative 0.154 to negative 0.010. And we could just check this for fun. Let's see, this would be a true proportion Z interval. So here we've got 150. Out of 365 and 180 out of 365. Confidence level of 95 gets the same thing.
Can we just do the calculations like on the calculator, or do you want us to do it by hand?
It's fine to use the calculator, and you should be able to plug the numbers into the formula as well, though. So you could just write it out as a formula, and then you could just use the calculator if you wanted, instead of typing everything in by hand into the calculator. All right. Any other questions?
So because 0 is not contained within this interval, would we decide to reject or not reject?
I would I would say that there is evidence to reject that these are equal. That the proportion of sunny days in Great Falls is equal to the proportion of sunny days in Missoula. And you can give a direction as well. So it looks to be like that there's a higher proportion of sunny days in Missoula than Great Falls. And I'll write this out a little more carefully here. So we can say what this means. We can say we are 95% confident that the proportion of sunny days in Missoula is between 0.01 and 0.154 higher than the proportion of sunny days in Great Falls. So yeah, I got rid of the negative sign there, and I just said what that negative sign told us was that it's sunnier in Missoula. So, and then we're 95% confident that it's between this and that proportion sunnier.
Is that because P2 is Missoula?
Yeah, because P2 is Missoula. So when we first started off this problem, we could have gone the other way and had P1 be Missoula and P2 be Great Falls, proportion for Great Falls. Either way is fine. But you would get the same conclusion with what that confidence interval would tell you. All right, so what do you guys think I should do next? Do you guys care?
Can we just go over like when to use pool to plan on it?
Oh yeah. Yeah. So when to use pooled? So you want to use pooled only if you have, well, in this class it's only with a hypothesis test for two proportions, and then you'd always use pooled then. So with the two samples with the means, there's an issue in that you have to assume that the standard deviations are also the same, which generally you don't know. So pretty much I would follow what's on your green and your green summary sheet and see like the one of them's pooled and the other one's aren't. Yeah. Any other questions?
But for confidence interval, would it be pooled?
Yeah, go ahead. Yeah.
Sorry.
Oh, go ahead.
For a confidence interval, would it be pooled then?
Nope, not pooled. Yeah, confidence interval, you don't have that assumption that the proportions are the same. So, or the standard deviations are the same. So, yeah, question back here.
So, on this grade sheet,
Mm-hmm.
for the means of test significance for two samples,
Mm-hmm.
there isn't, like, I assume the S underneath that equation stands for standard deviations. Or is it something else?
So was that the
T minus log R1 minus log R2 over the square root of S2 1 over N1 plus S2 2 over N1.
Oh yeah, so there's two different standard deviations from each of the samples. So yeah, you're right. The S1 is the standard deviation from the first sample, and S2 would be the standard deviation from the second sample. Yeah. All right. Any other questions? Do you want me to do one more problem? I could do one more problem. All right. Yeah. Go ahead.
I have a question about some other reviews with the TA reviews, like John has a few of them.
Oh yeah.
From like 3 to 7 and 3 to 5 and whatnot.
Yeah.
Those Q&As, are they gonna be similar to what we're doing right now, where he's gonna run through stuff? Or is it gonna be kind of like a study jam? Or we just kind of ask random questions while he's like in his office hours?
Yeah. So it'll be up in the 305. As far as my understanding is that he'll have open to some questions, and I'm not sure like if he'll have problems prepared or not. I'm not 100% sure with that. It sounded like it was kind of like a half and half kind of thing. Like he would do some kind of review, kind of like this, and then it would be half like you could work on some problems, and he would just be there. So that's what my understanding is. But, yeah. All right. Any other questions? I'll do. Oh, I forgot to do the type 1 error, so I got to do one of those before we go.
So in this test, is there going to be stuff on it from the beginning of the year, like from exam 1 or exam?
There may be. So look on the review, on the what you need to know. There was some things like sampling variability, and then knowing what like samples. There were some things, some basic things like how to know what kind of variable you have, like quantitative or categorical. So there might be some of those throwbacks, but the majority of the test and the majority of the points are going to be through. So what I'm saying is you may have like 5 points out of the 100, maybe some of that kind of stuff. So, all right. Yeah. It'll be 7 pages. I'm not. Yeah, pretty much. Yeah, and I don't have it nailed down yet with how many questions. So, shooting for 7 pages. So.
I mean, generally, I noticed you don't do a ton of partial credit, but with some of these longer problems, I understand they're all tied in together, so if you get one part of it wrong, you can generally get the whole thing wrong. But will you be giving any kind of partial credit?
Yeah.
Like
yeah, so there's partial credit, especially if it's a written answer. Those are good for partial credit. Also, some answers, maybe they'll be like 2 boxes and you have 2 blanks to fill in. And then, of course, each box would be half. Or if you show the work, then maybe partial for each of those halves. But then some questions are like like the yes, no's kind of thing. And then the multiple choice. The multiple choice generally are not partial credit. But the yes, no's, there's usually there could be several yes, no's in one problem, several parts to that, and that would be partial. But as a rule, always show your work. And if you're doing it correctly, then you would get partial credit for that. Also, just another kind of heuristic with the test is if you do one part and you just completely blank on the first part, but then you kind of know what to do for the second and third, just say we're going to use these numbers and then say what the answer would be with that. Just kind of show me what you know, kind of thing. So you could still fill out the second and third blank even if you don't have the first blank, so you don't have to feel like you just gotta give up. So, so yeah, I would highly encourage you to write, if you have time, write something down for each blank. Just try it. Any other questions? And then we can do the type 1 error. It's been like a long time since we talked about that. So let's, since we're on the, we gotta do type 1 and type 2 error. Since we're on this this problem, let's talk about what the so what would a type 1 error?
Yeah, it'll pop up on your screen.
Oh, that's fine. What would a type 1 error be for this problem, for this hypothesis test? Okay, so that would be if we say if we favor the alternative hypothesis when in fact the null hypothesis was true. So we favor the hypothesis that Missoula is sunnier than Great Falls, when in fact they are equally as sunny. All right. Let's make sure I got that right.
What page is that in the book?
It's page 256. I could just throw it on here too. So the way to read this is I remember it off of the truth. So here the null hypothesis is correct, but then we decide the alternative, and that's what I wrote down. And then the other way around is if we say that we fail to reject the null, but when in fact the alternative is true. So type 2 error. So yeah, these are really easy to get mixed up, but okay. So this one is we can just use the word favor. That's fine. So we favor the hypothesis that Missoula and Great Falls are equally sunny when in fact Missoula is sunnier than in Great Falls. All right, I think let's let's go ahead and end this review here, unless there's any last minute questions. And there'll be there's a study jam tomorrow, 10 a.m. to 1 p.m. and that's in the Lomason Center. Question? 2 to 3 p.m. My office hours. MA 205A. Yeah. Yeah. 205A. Yeah, 205. Second floor. Right up there. Okay. Yeah, thanks for coming. I was really impressed with the turnout. Thanks for all coming. So.